Okay, this is AP, AB, and BC Calculus. We're doing Unit 6, Section 6, which is applying properties of definite integrals. All right, so let's go right into the two slides that are going to have our different properties that we're going to work through today. So a definite integral is an integral that has bounds A and B. It doesn't have to be A and B, but in this particular instance, they're going to be A and B. So the first property, a sum or difference. So let's say you're integrating two functions inside a definite integral. You could have split them apart if they are a sum or difference. You can split them apart into a sum or difference of two integrals. So the integral from a to b of f of x plus or minus g of x dx could be split into the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. You can't do this with products and quotients, so it's important to note that that's not a possibility. So that works for a sum or a difference. If you have a constant multiple, where k is a constant, in front of an integral, you can yank that constant multiple out. So if you have the integral from a to b of some k times f of x dx, you can yank the k out and make it k times the integral from a to b of f of x dx. If you reverse the bounds on an integral, if you switch the bounds from a to b and switch them to b to a, you put a negative in front of the integral. And if you have some c that lives in between a and b, you can add adjacent intervals. So the integral from a to c of f of x dx plus the integral from c to b of f of x dx equals the integral from a to b of f of x dx. And I gave you a visual of what that looks like. If I were integrating the square root of x from 0 to 4 and from 4 to 7, I could put those two areas next to each other and make the entire area. Oops, my bad, that's a typo. That's not a 4, hold on. That's a 0 to 7. My bad, ignore my typo. 0 to 7. Oops. So again, the area from 0 to 4, the area from 4 to 7, and then, sorry, when I cut and pasted, I forgot to change the 4 to a 4 to 7, or a 0 to 7. Okay. So other properties of definite integrals. So the no width property. If an interval has no width, meaning that the top and bottom bounds are the same, then it also has no area. You have to have a width to have an area. So if you integrate from a to a of some function, you just get 0. There is a special rule for even functions. If a function is even, the way we define that is that f of negative x is the same as f of x, meaning it is symmetric about the y-axis. Easy thing to do is think of an x squared, right? If you integrate from negative a to a of f of x dx, it's just double what would happen if you integrate from 0 to a, because you can see that these two areas are the same, right? The blue area and the pink area are the same. So I could either do blue area to pink area and add them together, or I could just find this area and double it because they're the same area, right? A special rule for odd functions, so odd functions are symmetric about the origin, f of negative x equals negative f of x. An easy way to visualize that is x cubed. If you integrate from negative a to a of an odd function, you get 0 because you see how this is the same area as this, but this one is below the axis and this one is above the axis, so they net out and you get 0. Those really only come up if you're asked a question involving an even or an odd function, and usually they're called even or odd. Sometimes they're not, but if they don't tell you a function is even or odd, it probably means that you were given the equation, so you wouldn't have to know this rule. When you would need to know this rule is if they didn't give you the actual function and they were just referring to a function as some odd or even function without the function rule. All right, so let's go ahead and walk through evaluating some integrals given 3 other integrals. So I tell you that the integral from 3 to 5 of f of x dx is 9, the integral from 3 to 5 of g of x dx is -2, and the integral from 5 to 8 of f of x dx is 4. So let's find some things. So from 3 to 5 of g of x minus f of x, well, that's the same as integrating from 3 to 5 of g of x dx, which is an integral I know, minus the integral from 3 to 5 of f of x dx, which is also an integral I know. So that's a -2 minus a 9, which is a -11. Now, if you were able to skip to doing that in your head, congratulations, awesome. The integral from 3 to 5 of -10 g of x dx, well, I can yank that coefficient out, right? That constant can come out. And then I know the integral from 3 to 5 of g of x dx. It's a -2, so I get a 20. The integral from 8 to 3 of f of x. Well, this is tricky for 2 reasons, right? The first reason it's tricky is that I don't have any integrals by themselves that give me a 3 and an 8. I have 3 and 5, and I have 5 and 8. The second reason it's tricky is that the bounds are backwards. So the first thing I'm going to do is switch the bounds and make this a negative of the integral from 3 to 8 of f of x dx. And then I'm going to have to recognize that I can't really treat that as one integral. I have to treat that as 3 to 5 plus 5 to 8. So again, tricky for 2 reasons, because the negative and you have to split it apart. So that's a negative times, and then I know both of those things. That's a 9 plus a 4. So I get -13. All right, you go ahead and give this one a try. Again, if you don't need the same amount of work, if you're able to logic through what this should look like, congratulations, that's awesome. So in the first one, I'm going to split this into the integral from 1 to 6 of g of x dx plus the integral from 1 to 6 of f of x dx. And I'm going to recognize I know both of those numbers. That's a 4 plus a 10, so I get a 14. If you jumped from here to here, I'm cool with it. It's all good. This is not a problem where I would expect a lot of work. This is a problem where I expect you to be able to find the answer. Now this one's tricky because I reversed the bounds, right? So I'm going to go ahead and flip them back, right? So I'm going to recognize that this is actually a -2 to a 1 of a negative times 5f of x. So I get -5, the integral from -2 to 1 of f of x dx, right? And once I do that, that's this one, right, times a -5, so I think I get a 35. The other way to do it is to keep it in the order it's in and recognize that instead of being a -7, it would be a regular 7. Like, it would be fine to say, oh, I get it, this is a 5 times a regular 7 because the bounds are flipped. And then this one, I want -2 to 6 of f of x, but I don't have -2 to 6. I have -2 to 1 of f of x dx plus the integral from 1 to 6 of f of x dx. So I'm going to add this one to this one, so -7 plus 10, and I get a 3. Again, if you're skipping to the end on these, nobody thinks you're cheating. It's fine. I just want to show you how it works. All right. Given the graph of f of x and some values of definite integrals, evaluate. Okay, so if I'm integrating from 0 to 3 of g of x plus f of x, there's a couple things going on. The first thing I'm going to suggest you do is I'm going to suggest you switch the bounds, right? I'm going to make this the negative integral from 0 to 3. Sorry, I said 0 to 3 before and I meant 3 to 0. My brain is tired. I'm going to make this the negative of these things, right? And then the next trick is I need to split them apart into two different integrals. But notice the negative's in front of the whole thing. So if you split them apart, they now both have a negative. This is the negative of the integral from 0 to 3 of g of x dx, great, minus the integral from 0 to 3 of f of x dx. Now, I know this one. This is a 10. It's given, right? And I can find the integral from 0 to 3. So the integral from 0 to 3 for f is going to be this semicircle and this triangle, right? So I would suggest that somewhere you find some space and you just go ahead and find this integral, right? It's going to be, this is negative because below the axis, and this is positive, right? So it's going to be a negative 1/2 pi times 1 squared plus 1/2 1 times 2. So I think I get a negative pi over 2 plus 1. So that means that this integral is going to be a negative times the 10, and then a negative times this negative pi over 2 plus 1. So I get negative 10 plus pi over 2 minus 1. I get pi over 2 minus 11. All right, and then from 0 to 5 of f of x minus g of x, well, that's going to be the integral from 0 to 5 of f of x dx, which I can find in a sec, minus the integral from 0 to 5 of g of x dx. Now, that's a little tricky again, because, so we already found 0 to 3 for f. I'm going to argue that all you have to recognize is that you're just adding this chunk on, right? So I don't care how you want to add that chunk on, right? But you're going to need to find this integral. I'm going to argue that it is the existing value you already found, which was the negative pi over 2 plus 1, plus height of 1, base of 2, base of 4, so 1/2 of 1 times the sum of the bases, plus this one, which is again a height of 1, and this is a 3 and a 4, so 1/2 of 1 times 7. So I'm going to argue that you can find that this one is a negative pi over 2 plus 1, plus a 3 plus a 7/2. Super fun. So negative pi over 2 plus 8, which would be, plus 4, which would be 8 over 2. Sorry, that was what my brain was trying to jump to. So I get negative pi over 2 plus 15 over 2, and you can do what you want with that. That's this piece. And then for 0 to 5, I'm going to have to recognize that 0 to 5 is the sum of these. The integral from 0 to 5 of g of x dx would be this thing plus this thing, right? So 10 plus negative 2 is 8. So I get that that's an 8. So after all that, I get that this thing is an 8. So I'm going to get, so those are the two pieces. I'm going to get negative pi over 2 plus 15 halves minus 16 halves, right? Which seems to be negative pi over 2 minus 1/2. So there's a lot to them, right, even though these are pretty straightforward skills, and I'm intentionally making these kind of lengthy just so you get the gist of how to apply the properties. So go ahead and try a P2, same idea. Again, I made them a little tricky on purpose. So you'll see that I'm looking for -2 to 6 for f and g, and also 3 to 6 for f and g. So you might as well find those values if you want for f and g, or for f rather. So I'm going to go ahead and find -2 to 6 of f of x dx. I'm going to find that it's this thing, right, this circle. So that's going to be 1/2 pi times 2 squared, which is 4, right, plus this triangle has a height of -2 and a base of 3, so 1/2 base times height, right, plus this triangle has a base of 1 and a height of 2, so 1/2 1 times 2. So I'm pretty sure that I get that this chunk, just the f, right, just this f integral that I'm going to need, is a 2 pi minus 3 plus 1. So 2 pi minus 2. Great. So the reason that's useful, and by the same token, I would argue that you could just right now bust out that if you put these two together, the integral from -2 to 6 of g of x dx should be the sum of the -2 to 3 and the 3 to 6 integral. So I think that that should be -10 plus 3, which is a -7. So that means that this one is going to be the integral from -2 to 6 of f of x dx, which we just found, minus the integral from -2 to 6 of g of x dx, which seems to be a 2 pi minus 2 plus a 7, because it's minus a -7. So I think we get 2 pi plus 5. These are much nicer problems if I don't give you the circles, by the way. For this one, the bounds are reversed, right? So I'm going to flip it and make it a negative. I mean, there's a couple different ways you could do it. You could either flip it and make it negative, or you could just find the value. You could understand that g of x, when integrated from 6 to 3, is the opposite number, right? So there's a couple different ways to do this, right? I guess if you don't want to put the negative, another way to do this, right, is you know that g of x, when integrated from 3 to 6, was a -10, which means if you integrate from 6 to 3 of g of x dx, it's a regular 10. And you could play the same game with f, right? If you integrate f, so by the same token, if I integrate f from 3 to 6, right, it's going to be this chunk right here and this chunk here. So there's a couple different ways to do that, right? I would argue that these two triangles net 0. So really it's just this area, right? And just to show you why I say that, this is a 2 by 1 triangle, right? And this is a 2 by 1 triangle. This one's negative, this one's positive. So they just net 0. So this is the area I want, right? So basically I can find that f of x area by saying, oh, it's a negative area. It's 1/2 the height times the sum of the bases, right? It's 1 plus 2, but it's the whole thing's negative because it's below the axis, so it's a -3/2. If I know that, right, then that means that the integral from 6 to 3 of f of x dx is just the negative version of that, so a negative of a negative is a positive. So this ends up being the integral from 6 to 3 of g of x, which we just saw was a +10, and the integral from 6 to 3 of f of x, which we see is a 3/2, right? So that's 20 halves and 3/2, so 23 halves. That's the gist of it. All right, couple more. All right, so let's do some integration around removable discontinuities. So it's really helpful if you sketch a graph of what this looks like. And I know you're probably not stoked about that. Like I turn to this page and you're like, oh, great, sketching a graph of a piecewise function. But let's look at this for a second and see what's happening. If you factor the top here, you get x plus 1 times x plus 2 over x plus 1. Look what happens to this. There's a hole at x is -1. This thing just behaves like an x plus 2. This graph looks like this all the time. So this graph looks like this all the time except at -1. So I'm going to do a terrible job of drawing this line because we've all established that I shouldn't be allowed to graph things. That's what this looks like, and then this piece of information tells you that this hole is plugged right here. That's it. So now, if you realize that, let's look at what they're asking. They're asking me to find the integral from 0 to 4 of this thing, right? That's it. They just want the area of this trapezoid. It's just a line. It looks complicated, but it's not. It's just, this is a line, so it's a trapezoid. The bases are 2 and 6. The height is 4. So this is 1/2 the height times the sum of the bases, right? Which is 1/2 of a 32 or a 16. All right. And I did say around removable discontinuities. In this one, I accidentally didn't make you do it around the removable discontinuity. It was a poor choice. I should have made you do something on this side, but oh well, you get the idea. So this one actually wasn't integrating around a removable discontinuity because it didn't actually touch on this interval, but the next one will, so my bad. All right, so same idea, right? I want you to integrate from 0 to 4, right? And this time the removable discontinuity is in the right spot, so yay. Okay, so let's look at this thing, right? If I factor this, right, if I factor x, I can go ahead and make an educated guess that there's an x minus 2 on the top because it seems likely that since there's that x minus 2 on the bottom, and sure enough, there is, and there's a hole. So this thing just behaves like x plus 1, except at 2. So x plus 1, but at 2, there's a hole, right, because there's a hole at 2. But it's just going to behave like this, right? So it looks like this forever and always. I'm just not going to do a very good job of it because we've all seen that. But then this piece is saying that this plugs the hole. You're being asked to integrate, sorry, my bad. You're being asked to integrate from 0 to 4. So that's from here to here. Well, that's just a trapezoid, and the hole's plugged, so you're all good, right? So one base is 1, the other one is 5, and the height seems to be 4. So this is going to be 1/2 the height times the sum of the bases, right? Which is 1/2 of 24, or 12, and that's it. And again, on the last example, I meant very much to have you integrate around the removable discontinuity, but sometimes these things happen. All right, moving on. All right, integrating around a jump discontinuity. So again, this is going to be really helpful if you sketch this graph. So when I sketch this graph, and we've kind of seen this before, but piecewise functions, absolute values are actually fundamentally a piecewise function, okay? Basically what's happening is if I find when 4 minus 2x equals 0, I get that it's when 4 equals 2x, which is when x equals 2, right? And actually, I can do you one better. It's not just when it's equal. Let's clean that up a little bit. When the inside of an absolute value, right, if the inside is greater than or equal to 0, right, then the absolute value doesn't do anything, right? So if the inside of the absolute value is greater than or equal to 0, so when 4 minus 2x is greater than or equal to 0, which is when negative 2x is greater than or equal to negative 4, or when x is less than or equal to 2, the absolute value doesn't do anything. So this thing is actually a piecewise function. Basically, it just behaves like a 4 minus 2x over an x minus 2 for x values that are less than 2. We'll talk about the issue at 2 in a second, and I'll talk about why I didn't put the equal to. And then for other values, right, for x is greater than 2, it's going to behave as the opposite of what's in the absolute value. So it's going to behave as a negative times a 4 minus 2x over this x minus 2. Now, why did I leave out the x, the x is 2 value? Well, because there's a problem with plugging in 2 on the bottom, right? If I clean up both of those, so let me just make the pen a little smaller so we have something to deal with. So let's jump down here for a second, clean that up. That means that f of x is behaving as, if I yank out a negative 2 times x minus 2, I can cancel an x minus 2. It's behaving as a negative 2 for x values less than 2, right? And if I yank out a negative 2 here as well, I get a negative times a negative 2, which would be a positive 2, times x minus 2 over x minus 2. So basically what's happening, and we've seen this graph before when we did limits, is that this piecewise function is behaving as two horizontal lines. It's behaving as negative 2 for x values less than 2, and it's behaving as 2 for x values greater than 2, right? That's what's happening here. So what's going on, and you can actually see that, right? If you tried plugging in, try plugging in 0. If you plug in 0, you get the absolute value of 4 over negative 2, which is a negative 2. If you try plugging in, let's say 10, right, you get the absolute value of negative 16, which is a positive 16, over an 8, so you get a positive 2. So basically, this is what's happening. The graph looks like this until 2, and then after 2, it looks like this. So now, if you're asked to find the area of this, right, if you're asked to integrate from 0 to 5, right, well, that's this rectangle and this rectangle. This one's negative because below the x-axis, this one's positive. So what's going to happen is my area, you can actually physically just count the boxes. This thing is a negative 4 because there are 4 boxes there. This thing is a positive 6, so it's negative 4 and positive 6, which is an area of 2. So the trick is that you can't really integrate this just looking at it. You have to visually see what the graph is and look at the areas. So you have to look at this and say, okay, this is what this value is. It's definitely a trick question. It often comes up as multiple choice. All right, so this is the easiest version of this question, so in P4, only because I've told you this one before. This one behaves like -1 if you plug in values before 0, and behaves like 1 after 0. And if you already had that memorized, it's really useful. If you didn't, the only way to spot it is to recognize that it behaves as the opposite of x for values where x is negative, which would just be a -1, right? And it behaves as itself for x values where x is positive, which would just be a 1. Once you know that, you're integrating from -3 to 1. Well, that's this box, right, which is 3 boxes. So this area is -3 because it's literally 1, 2, 3 boxes below the axis. And this is 1 box. So that's a +1. So this is going to be -3 plus 1, which would be a -2. Okay? And again, how much of that, like all of this work that went into this, I don't need that if it's me doing it because I've seen this graph a million times. Honestly, if you spot this trick, if you spot that it's one of this kind of question, the easiest thing to do is just plug in a couple values to the left and right of that value, like so you can see 0 is the problem, right? If you look at this, you can see the problem's at 0. If you can't remember which side is above 0 and which side's below, you could just pick a couple numbers. Like you could say, oh, I know that 0 is the issue. So what happens if I plug in x is -1? Well, I'd get the absolute value of -1 over a -1. Hey, that's -1. That must mean this whole side is -1. And if I plug in x is 1, I get 1 over 1. Oh, hey, that's 1. That means this whole side's +1, and then you can just sketch the graph. So that's the gist.